Hello and welcome back to the course. So today we start looking at mechanical vibrations. We're splitting this section into two parts. There's section 2.4 in the book, and we're going to look at where it comes up, and we're going to look at the free undamped motion, and we'll do the damped part next time. All right, so the book is you can get it at this URL. You can either look at it on the web, or there's a PDF version of the book, or you can um, get a paperback if you want. But the PDF is free, so you can just use that. All right. So what are we doing? So we're looking on like the diagram of the setup is over here, right? So here's some mass, and it's attached to some wall by a spring, right? And it can move like back and forth, right? So along the floor, and there might or might not be some friction. So maybe you could think of wheels on this mass, or maybe the floor is, you know, as very well waxed, so everything slides on it or something. Um, so that's the idea, right? So now all the variables are, so t, we're gonna have the time in seconds. X is the displacement, so x is at x equals 0 is the rest position. That's where the spring is where it would be if there's no tension on it, right? And so that's where the mass is, and it's if it moves this direction, that's in the positive direction. This direction is the negative direction. So by positive direction, I mean x is positive when it's pulling the spring, and negative when it's sort of pushing the string into the wall. Now, m, we're gonna, when we use it as a variable, that's the mass in kilograms. K, that's the spring constant. It's in newtons per meter. It's how you compress this. Like the more you compress it, the higher force it puts out, right? And C is the damping. So maybe friction, or maybe like there's a damper attached to this mass that's sort of slowing everything down, and then it's in newton seconds per meter. That's those are units here. And F, this capital F, well, that's just some external force acting on this M. If it's positive, it's pulling it in the positive direction, right? All right, so how do we set up this, how do we set up the equation that this is supposed to satisfy, right? It should be equation for x, right? So first, we look at Hooke's law, which is what the spring does. So the force exerted by the spring is proportional to the compression of the spring, or to how far you pull it. And it goes I guess in the negative direction, you know, from x. If x is positive, then it's pulling in the negative direction, and the x is really how far you've pulled it, or maybe if x is negative, how far you've compressed it into the wall, right? So that's the force from Hooke's law. Then from damping, well, I mean, damping is proportional to the velocity. That's just, if you think friction, right? It's really, the faster it goes, the more of a, the more damping there is. So, and again, it's in the opposite direction of the velocity, so it's proportional to the velocity. So it's some constant times the velocity, well, with a minus sign because it goes in the opposite direction, right? If the velocity, if it's going away from the wall, of course the friction is pushing back on it, right? Now, Newton's second law says that force is equal mass times acceleration. So mass times acceleration is m times x double prime, the acceleration, right? And that's supposed to be the total force on this mass. So that's F, the external force, and then minus c times x prime, the part of the force coming from the damping, and the part of the force coming from the spring, right? So we have this equation over here, which we could sort of rearrange and get this equation out here. And of course, notice that m, c, and k are just constants. So this is a second order, because there's a second order derivative here. It's linear constant coefficient ODE, right? Because m, c, and k are constants. All right, so the terminology that we'll use is that we'll say the motion, the system is forced if this function f is not identical 0. And by not identical 0, what we mean is that it could be 0 at some points, right? But that it's not always 0, right? So that's what we mean by these 3 lines over here. And when we say not identically 0, right? And maybe it's 0 somewhere, but at some times it's 0, but it's not always 0. Then it's forced, right? There's some external force. It's unforced or free if this f is 0, and that's actually what we're going to consider in this section. Just free. All right. Now we're going to say it's damped if c is positive, and it's undamped if c is 0, right? So notice here, that's actually somewhat important, is that m, c, and k are all positive numbers, right? All right. Now let's look at another place where this comes up. So if the mass on a spring, applications like that come up all the time that are maybe similar to mass on a spring. It could be you're considering maybe the behavior of a building in an earthquake or stuff like that, right? That might actually look sort of like mass on a spring, but it comes up in other contexts as well. So, for example, in a so-called RLC circuit, right? So you have RLC is that it's from these 3 letters over here. You have a resistor of R ohms. You have an inductor of L henries, and you have a capacitor of C farads. Right? And then there's an electrical source, and that is E volts, and that can possibly change in time. Right? Now, in such a circuit, we measure, or we can measure more things, but we can measure 2 things: the charge on the capacitor, how much charge is there, and what's the current flowing through the circuit, right? So we'll use Q and I for those, and those again can change with time, right? Now the basic relationships are that the change in the charge is equal to the current flowing through the circuit, which makes sense. If the capacitor is charging or discharging, that's what's happening, right? And then sort of basic, let's not go through the through the basics of this, but basic principles will tell you that there's this this equation over here. Now, that's not quite the equation that we're looking for, but what we could differentiate. Notice that L, R, and C are constants, and if we differentiate, we're gonna get I double prime out here. We're gonna get I prime, and then we're gonna get Q prime, and Q prime is just I, right? So we're gonna get this this guy over here, which is a second order linear constant coefficient ODE, right? And it's precisely of the same sort. LR and 1 over C are going to be some positive constants, and here the outside, or what was the outside force, the external force on the mass is the change in voltage, right? And so we're going to get sort of similar behavior as the mass on a spring. At least the mathematical analysis is going to be the same as mass on a spring or the RLC circuit. And you get, just like on the mass on a spring, we get if the resistance is low, or that corresponded to the damping being low. So we're going to get some oscillatory behavior, right? It's the mass on a spring is going to oscillate back and forth, right? You've seen this sort of stuff before, right? You have a spring and you sort of, tweak it and it just goes back and forth, right? Especially if there's not that much damping, right? So you're going to get the same sort of oscillation out here, right? Okay. And it's going to be unforced if the voltage is not changing. All right, now a third example might be, I mean, in some sense a little simpler, in some sense a little more complicated, and it's going to be the pendulum, and it's really the linearized pendulum is what we'll study in this section. So suppose that we have a pendulum. That means a mass on some long stick or a string, and it's attached somewhere at the ceiling, right? Or somewhere it has a hinge or something, and it's allowed to move back and forth, right? So that's a pendulum. Now we have so there's mass again, m, like some kilograms or whatever. Let's not worry about the units here. Then we have theta, which would be the angle of the pendulum, and let's think that angle 0 would be that the pendulum is hanging straight down, and positive theta is in one direction, negative theta is in the other direction. So that's my theta. Again, it depends on t, right? And that's really going to be what we're going to be solving for. Then there's going to be L, which is the length of the pendulum, and G, well, there's some force of gravity. Gravity is the thing that's going to make the pendulum swim back and forth. So how do we, how do we get the equation? Well, it's again Newton's second, right? So really the main thing is, well, there's gravity, which is mass times the gravitational constant G, right? That's going to give you the force that's going straight down. Now that's not the thing that's acting on the mass, right? Because, well, the mass is on this stick or string or whatever it is, so it can't just push it straight, pull it straight down. It's only, the mass can only move along this circular arc, right? So we're looking only at the component of the force of gravity along, so tangent to this well, where the mass can move in this arc. And that's given, if you do just a little bit of trigonometry, that's really sine of theta times the force of gravity, right? So for example, you can see that it's correct, is that if the pendulum would be straight down, the mass would be out here at the bottom, then there should be no force from gravity because, well, it's completely straight down. It's not going to be, like if you have the pendulum hanging straight down, it's not going to move, unless you push it or it has some initial velocity or something, right? But if you just, hang the pendulum, hold it for a little bit, let go, it's not going to start moving, right? Because there's no force acting on, well, even though there is, but it's counteracted by this rod is pulling back up on it, right? Okay, so that's the force acting on the mass from gravity, and you could think of it as going in the negative direction, because if theta is going in the positive direction, this is pulling back, right? So it's really minus mg sine of theta, right? So that's the force that's supposed to equal mass times acceleration, which is m, and acceleration is, well, acceleration you want to think about in units of distance in seconds squared, let's say, in time units squared, right? Now to get the distance along the arc, right, you take the radians times the radius, right? So the radius is L, right? And the radians is theta, and you differentiate that twice, and you get L times theta second derivative, right? So you have m times L times second derivative of theta is equal to minus mg sine of theta. I can rearrange this a little bit, and get the following equation. And now that's not linear, right? It's not linear because this is a sine of theta, right? It's the theta is not showing up linearly, showing up very non-linearly. This is actually a complicated equation to solve, and it's not one that we've looked at in this chapter, right? We've only looked at really the only ones that we could really solve were constant coefficients, and maybe some other ones in the or in the exercise in the book, but this is not one of them. We've only looked at linear ones anyway, and this is definitely not linear. But for small theta, we get this. We get that theta is really same as sine of theta. If I graph both, I get, well, this is a graph from -1 to 1. So you can see that the slightly curvy blue line, right? That's sine, right? And I'm only looking at near 0. And the straight line, that's just theta, right? So the vertical axis is theta. The vertical axis is well, whatever it is, and the horizontal axis is theta. Sorry. So when theta is 1, well, theta is 1, and sine of theta is slightly less, right? So over here, it's already kind of bad, but like maybe from -5 to 5 to 0.5, so -0.5, sorry, to 0.5 in this region, it's actually pretty good. And maybe if I look at it even a smaller region, it's even better. So near 0, we get this thing. And that's really coming from the linearization that you did in Calc 1, where you do a linear approximation of a function in terms of its derivative, right? So this is precisely the reason why you'd want to do something like that. It's this is a very complicated equation, but if we replace the sine of theta by theta, then we get this much easier equation, this linear equation, right? So we've linearized this equation, right? So this is where maybe the way that you were seeing it in Calc 1 didn't seem like all that useful, but this is where it really becomes useful, right? So so that you can approximate this behavior by this, well, as long as the theta is not too big. So if you have a pendulum and the swings are not that big, right, in terms of angle, right? So it's a long pendulum and it's not swinging that far out. This is a very good approximation of the behavior of the pendulum. Maybe not for a very long time, but for a short enough time frame, this is going to be good enough. Now, if the swings are very big, then yeah, it's not going to be as precise. But as long as the swings are small, this is a reasonable approximation, right? As long as you're not doing it for a very long time, because if in each swing you get a little bit of an error after a while, those errors add up, right? So, but for some reasonable time frames, and reasonably small swings. So, and the shorter the swings, the longer time frame will be good enough. So you get this equation out here, which is much easier, which we know exactly how to solve, right? And so we'll consider just free motion. So meaning, as I said, just f is just identically 0. And what we'll start with is free undamped motion. So the damped motion we'll leave for the next lecture. But this time we're only going to look at c equals 0. So there's no c times x prime in this equation, right? So we're going to study this guy. Now, what we could do is we could divide by m, and then we'd have in front of the x we get k over m, and we could write it as omega naught squared, where omega naught will write like this. And you'll see in a moment why that makes sense to take the square root. So we could write the equation like this, and this omega naught is going to have some nice physical interpretation. And by the way, so we've looked at the other applications. We're just going to write everything in terms of the original mass spring thing, right? We're going to keep that in mind. And, whenever I say anything, it's going to be, referring back to the mass spring model. All right. So we're going to write the equation like this. And so we get the solution is this simple harmonic motion. And it has this formula. You have some constant A, arbitrary constant A, times cosine of omega naught t plus b sine omega naught t. So you can see why that makes sense, because normally you'd have a square root or whatever was in front of the x. That would come from solving the characteristic equation here, right? So you have this formula. You can rewrite it. I mean, this is, when you might say, well, it's a sum of a cosine and sum of a sine, but of the same frequencies, and that's just going to be another sine wave or cosine wave, however you want to call them. So you can, by doing some trig identities, let's not worry about the trig identity, but you can try to figure this out, how that would work by applying various trig identities. You can write it as this, right? With a cosine. You could do it with a sine as well, but let's do it with a cosine. So now the arbitrary constants here are c and gamma, right? And so you just have one cosine, with one coefficient in front, but now you're also allowing this shifting. You're allowing to shift along the dependent axis, right? You're shifting the graph. That's basically what changing these a's and b's does. It's changing this c and also shifting along, but it's still going to be a sine wave or cosine wave. That's actually the frequency. All right. Now this form, that's what you would normally get from what we were doing, right? That's how you would write down the equation. And that's actually very nice for solving for initial conditions. If I have initial conditions that I want to solve for, that's really easy in this form, right? Because it's really easy to plug in, especially if t is at 0, right? That's the initial time, because then if you plug in t equals 0 over here, right, you just get cosine of 0, which is 1, and sine of 0, which is 0. So you just get a, and it's a similar thing for the prime, right? So you can just sort of read off the a and the b in terms of the initial conditions. So that's the usefulness of this form. This form, on the other hand, is useful in that this c and this gamma have natural interpretations. So let's go through interpretations of these constants c, omega naught, and gamma. Right. So omega naught is the angular frequency of the motion. Right. And so it's not in cycles per time, but it's radians per time. How many radians does the thing move per unit of time? Now, it's we call it natural angular frequency, but right now that doesn't really it doesn't make a huge difference. Later on, when we looked at the damped, there's going to be a difference between the natural frequency and the actual frequency. But right now, there's no difference, and so it's just the frequency, or you can say it's the natural frequency. Now this C is the amplitude, and you can compute it in terms of the A and the B. If you figure out this trig identity that goes between here and here, that's going to give you this formula. That's the amplitude. That's how far. This is a wave, so it goes up and down, and it has certain amplitude, right? So how far it goes in each direction, right? So it goes from minus C to C, right? Because that's so cosine will go from -1 to 1. So if you multiply by c, it goes from -c to c. So it's the amplitude of these waves, right? Of these sine waves. And gamma is the phase shift. So all it does is basically it takes this wave and it moves this sort of back and forth along the time axis, but it doesn't change the frequency or the amplitude. And a lot of times it's maybe not as important because it's just everything gets just shifted a little bit in time, right? But same amplitude. And sometimes you're interested in it, and sometimes you're not that worried about the phase shift exactly. All right, unless you're interested in exactly when when you're at some point of this motion. But a lot of times you might be actually interested in not in the actual solution. You might be interested in the omega naught, or you might be interested in the c. Those are common things to ask for, right? So now, so this was angular frequency, so radians per unit time. Usually when you say frequency, it's cycles per unit time. So if I'm on the way, if the mass is all the way at the end, right? If I'm at one point of the cycle, if I let it go all the way down and then back up, that's going to be at the other end of the cycle, right? So that's one cycle. It's this going back and forth, right? And then it just keeps repeating that, right? So each one of these is a cycle, right? So if you want the standard frequency, which would be cycles per unit time. So for example, cycles per second are hertz. So you've clearly, you've surely heard of, hertz referring to frequency, right? So megahertz, right? Right. So if we want to get the frequency, well, we have to divide by 2 pi because that's how many radians there are per cycle. So if you have the radian, the angular frequency, sorry, you divide by the radians per cycle, you get the cycles per unit time, right? So for example, if you had the angular frequency in radians per second and you divide by 2 pi, you get cycles per second or hertz, right? Now, 1 over the frequency is the period, right? That's the time for one cycle, and that's just 2 pi over omega naught, right? It's just 1 over this, right? So if you want to take how long, if you don't know how long it takes for the mass to go from one extreme, back to the extreme and back to the first extreme, well, that would be a period, right? So, and that's 1 over the frequency, or 2 pi over the angular frequency. Now, before we go on, let's look at certain animation of this. All right, so we have this animation over here. Here I've put in the mass vertically, but the same thing is just because I have x plotted vertically and time plotted horizontally, right? So the horizontal axis is time, the vertical axis is x, right? And you can see what the graph, how it how it relates to how the mass is moving, right? So we have as time keeps going forward, we get this sine wave, and that's precisely how the mass is moving, right? So you can think of this, maybe the x-axis being sort of horizontal, maybe looking at this from the top, right? And then that's the motion it makes, right? So let's look at an example, a specific example where we let m be 2 kilograms and k is 8 newtons per meter. And suppose this entire setup with the mass and the spring and so on is sitting on top of a truck, and it's sort of facing forward, right? And the truck is moving at 1 meters per second, and then it crashes into the wall, right? So it suddenly stops. It's everything just goes to a halt, except the mass, of course, which is sitting on on this setup, and it was fixed at some point at because it was, well, when you packed it onto the truck, you make sure to sort of tie it down or something. But when the truck crashed, it breaks loose, so it's still on the spring, right? And it was half a meter in front of the rest position, so the spring was stretched a little bit, and it gets loose during the crash, and it's the mass is continuing moving because there wasn't any wall in front of the mass itself. It was on top of the truck, and the truck crashed, so the truck is stopped, right? But this was on top of the truck, maybe a little bit back, and so now the mass is moving forward at 1 meters per second because that's how fast it was moving, when it was on top of the truck, fixed. So now this mass is going to start oscillating, right? And so what is the frequency of this oscillation? And what is the amplitude? How far does the mass go forward before it starts going backwards, right? And how far it goes backwards before it starts going forwards. So what is the amplitude? So the problem is this, right? So there's no C, there's no damping. Mass is 2, K is 8, right? Mass is 2, K is 8. The initial position was 1/2. The initial velocity was 1, right? And so the angular frequency, well, it's just K over M, square root of that. K over M, it's 8 over 2, that's 4. Square root of 4 is 2, right? So the angular frequency is 2. The frequency in hertz, which is probably what we're thinking of, is 2 over 2 pi, or 1 over pi, just roughly 0.318, right? So, for example, it would, you would do 0.318 cycles within 1 second. So in 10 seconds, you would do like 3.18 cycles, right? Or in 100 seconds, you would do 31.8 cycles, right? And in 1,000 seconds, you would do 318 cycles approximately, right? So that's frequency. Now, the general solution is, so if we want the amplitude, right? So we figured out the frequency. That was easy. The amplitude is a little bit more complicated, and that the amplitude does depend on these initial conditions, right? So again, as I said, the easier form to solve for the initial condition is this one, where you have the A and the B and just the cosine and the sine, right? So if I plug in, right, if I plug in 0, I just get A is a half, right? Plug in 0, this cosine is just 1, this sine is just 0, so I get A, and it's supposed to be a half, so A is a half. Now, so A is a half, I could plug that in, right? And I could take the derivative and plug in 0, right? So if I, this is the derivative. If I plug in 0, I'm supposed to get 1, all right? And then the derivative, well, I'm getting this 2b, right? So if I differentiate, right, I get this cosine. Now, if I plug in 0, this just goes away. Maybe, I have too much orange here. So this goes away when I plug in 0 because the sine is just going to be 0, and this is going to be 1. So I have 2b is 1. That means that b is a half, right? So again, we've done this a whole bunch of times by now. So, all right, so the amplitude is the a squared plus b squared square root, right? So a was a half, b was a half, so a squared is a quarter, b squared is a quarter, quarter plus quarter is a half, square root of that, square root of a half, approximately 0.0, so 0.707 meters, right? So that's the amplitude. That's how much, how much forward from the rest position is sort of the extreme, how far it will go, right? And it will go there, and then it will go back. And it will take approximately, I guess, a little bit over 3 seconds to complete one cycle. All right. And the solution is this, right? So I just plug that in and I graphed it. And actually, the animation that I showed you before, that's actually, you can find it animation on the website under the Sage demos. That animation was precisely with these with these constants. If you look at the scales, that's where it was. But essentially, it's just a sine wave, right? And maybe it's not completely easy that this is going to be 0.707, but you can see 0.5 is over here, 1 is over here. Yeah, so 707 is going to be somewhere over here, right? Okay. All right. So in general, free undamped motion. It has this solution where this is the natural frequency and the angular frequency, and then the initial condition is x at 0 is a, and x prime at 0. Okay, so one of these omega nodes will come out. So the initial velocity is omega naught times b. So you can solve for either the initial velocity or b, one from the other. So amplitude, we've already seen, that's a squared plus b squared, square root of that. Now, one thing that we haven't talked about is gamma, and it's a little bit harder. So if you think of, so if you figure out if you look at the trigonometric identity that goes from this form to the c cosine of omega naught t plus minus gamma form, you're going to note that gamma, the tangent of gamma is b over a, which is precisely this same equation that you get, for example, for polar coordinates. If you're figuring out the angle in polar coordinates from the point, in this case, AB, right? You would get precisely this same equation. And solving that is it's not too bad. It's there's a small trick. So one takes the arctangent, but that could be a pi off, right? So you might have to add pi after taking the arctangent. And it's really because over here, like you lose the sign of a and b, right? If a is positive and b is negative, if a is positive and b is positive, then it's the same thing as if you take minus of both, right? If a is 1 and b is 1, b over a is the same thing as if a is minus 1 and b is minus 1, right? So you cannot tell between those two, those two a's and b's, right? So what you have to do is basically you have to look at where which quadrant you're looking at. So in the example, we had a and b were equal, they were both 0.5. So tangent of gamma was 1, arctangent of 1 is pi over 4. So is gamma pi over 4? Well, we still have to check something. So we have to look at which quadrant we are in. So A and B are both positive. Really, what's important is that A is positive. And so A and B is in the first quadrant, so we don't need to add pi. And gamma really is pi over 4, right? Now, basically the argument is that if A is positive, you don't add pi. If A is negative, you add or subtract pi. Either one will do. And if A is 0, okay, then just think a little bit. But if A is 0, well, and this made no sense. You didn't even get here, right? You can't divide. But if A is 0, then if B is positive, then gamma is actually pi over 2. And if B is negative, then gamma is minus pi over 2. Again, this is just like what you do in polar coordinates, right? And there are, calculators or computer software often has this, some function that, might be named a tan2. That's a common name for this, where instead of giving it b over a, you give it both a and b, and it will just, do this checking for you, right? So it's basically, finding, well, I mean, give me the give me the relevant angle for that point AB, right? So, but again, as I said, gamma is, I mean, if you're looking for the specific solution for, so you can plug in and draw, but then you might as well just draw this, right? And often, when you look at the other form, it's usually you're interested in C and omega naught, and so not necessarily gamma is gamma doesn't come up so often. That's what I'm trying to say. All right, so next time, what we're going to look at is well, we're basically going to add damping and see what it does, right? Okay, so see you then.